Yeah. Yeah. So Henry's law effectively says that if I have a gas, that it's going to uh, dissolve inside of a liquid at some proportion at a given pressure. And when I return it to that pressure, it's going to be dissolved at that same proportion. So, and it's all dependent upon that gas's solubility factor and stuff like that. So what it means is like when when you have a gas mixture that returns to 1 atmosphere, you're going to have, you know, the same amount of nitrogen dissolved in that type of liquid, that same type of liquid at 1 atmosphere. It's not going to be any different. Does that make sense?
Yep.
Okay, and then Dalton's laws pretty much says that, hey, if I got multiple gases, they're going to exert the same amount of pressure based upon their percentage in the gas mixture. And that's pretty much all those two laws are saying. So, and then the ideal gas law is, you know, pressure volume 1 equals pressure volume 2, and you throw a couple T's in there too. And that's just effectively showing you some adiabatic heating and cooling and throwing some volume in there as well. So let me do full screen here. Nope, that's not what I wanted. I wanted to do escape. I want to do view slideshow. There we go. That's more better. All right. So this is the relationship between pressure, volume, and temperature, right? Notice there's not depth, right? So, you know, you guys can kind of see these two, how they're related with filling a cylinder, right? If you jam a bunch of big volume into a smaller volume, like pressure will go up, and also temperature will go up. Right, that's called adiabatic heating. Right, those two variables will change, and they're the pressure and the volume is proportionally related to the pressure and the volume of the initial is proportionally related to the pressure and the volume of the final state, and then inversely proportional to the temperature. So yeah. All right.
What's the 1 and the 2 mean?
Initial and final.
Oh, 1 is the initial, 2 is final. That's so it's just there's no mathematics that you're doing with that. It's just notation.
You do yeah, what you really want to do with a lot of these things is arrow analysis. So like if I wanted to say, hey, say for instance, I have my pressure goes up and volume in there, and this is gonna move, and the rest of it, this stays the same, and this stays the same, and they'll say this stays the same and this stays the same. What's going to happen to my volume over there? Well, because they're proportional, your volume would have to go up.
Okay.
Right. Or conversely, if this stayed the same, right, then your temperature would have to go down to balance the equation, to make everything the same.
Okay. No, I'm very confused. This is why I should have gone to college.
I didn't go to college learning this stuff. Yeah. So that's how it's like it's proportionally related. This is called arrow analysis to qualitatively understand what's going to happen. And then you could do math with it, but you're not going to be asked to.
Okay.
Not in this one, this class. But they just want to have a general understanding of the relationships between all these things. and they break it down even more, even simpler, more simple. Let's see where to go. It was this
Chrome window.
This one, yeah, it was this one. Okay. Okay. Yeah, that's pretty much what I talked about. All right, so PV equals nRT. N is just the number of moles. Don't worry about atomic and subatomic particles, nothing. Yet you're not going to worry about that too much. That's just how the other thing is dissected. So you can use this if, like, this is a good one for a cylinder, right? If the number of moles is going to be the same, R is a universal gas constant, so that's not going to be, it's going to be the same. So if your pressure went up and your volume stayed the same, your temperature is going to go up as well, right? So to balance this change equation, right? That's what you see with adiabatic heating, right? When you fill a cylinder really quickly, your pressure goes up quickly, your temperature is going to go up because your volume effectively stayed the same inside the cylinder. That makes sense?
Yep.
Okay. All right, so partial pressure is the pressure exerted by a mixture of gases and the equal sum of its component, right? That's a lot of words for what I'm trying to show you guys mathematically. It's a lot easier to show this mathematically than with words, because words are confusing sometimes. So here's what it's telling you, right? And I showed you guys this on the whiteboard in the what do you call it, in on my video here. Ambient pressure is the atmospheres, the feet, right? And if it's oxygen, it's 0.21 at 1 atmosphere, 0.42 at 2 atmospheres, 0.63. Is that right? That's not right. Yeah, that's right. 0.63 atmospheres, and then 0.84. And you just multiply it by the number of atmospheres, right? And then 0.79 times 2, 0.79 times 3, 0.79 times 4, and so on and so forth, right? When I do this, I just do 0.20 and 0.80 because it makes the math easier. But this is just showing you that you multiply it by the number of atmospheres, and that's going to give you the partial pressure of the gas. Pretty simple.
Yep.
Any questions on that? Okay, moving on. All right, so yeah, you guys understand what this with nitrox. I've kind of beat this dead. All right, yeah, you guys understand this. I taught you nitrox, so you guys understand this. Again, understand this. Understand partial pressure in nitrox. Yep, you guys understand all this stuff. Any questions on all this stuff and how to calculate partial pressures, like with this stuff? I'm going to show you an easier way to calculate equivalent air depth. Okay, so this is kind of cool. I demonstrated this to you before using the 0.2 and the 0.8, and it actually comes out to be the exact same number, showing you, hey, dive in with an 80% nitrogen mix is this at 66 feet is same nitrogen exposure as diving to 99 feet with a 60% nitrogen mix. So that's where like the equivalent air depths come up with. Back in the day,
Isn't that
before
the
these nitrogen
number
came out.
on the oxygen side? Isn't that 1.6 like your limit on the partial pressure for oxygen at 40? So you wouldn't really want to go the 90.
Yeah, right. That's exactly true, and that's where my prelude is to when I'm teaching nitrox, or I'm teaching nitrox to people. I'm like, man, this is great. Well, why wouldn't I just go 100% oxygen? And that's where I lead into, because you have to manage your oxygen exposure. This is where you have to. This is where you got to talk into when you're teaching people no decompression limits. That's a function of the nitrogen partial pressure dissolved in your body, and the rate at which you ascend. Right, that's how you control nitrogen exposure, and that's what you learn in open water. and they may not have, recognized that. They just know that they can't stay down too long and they can't go up too fast because that's what their instructor told them. But in doing so, they are managing nitrogen exposure and managing their off gas rate by listening to their computers. So when you show them that, you tell them like, hey, this is what you're actually doing, is you're managing your nitrogen exposure by doing those things. Now, since you're breathing a toxic gas, because oxygen is toxic at certain partial pressures, you have to manage that, because we are teaching you to breathe oxygen all the way up to 40%, and that is within the realm of recreational diving. That is within the realm of recreational diving. We didn't care about it during regular open water. It was a scam, likely. Thanks for answering it for me. I'll see you when you go to bed. So yeah, here you go. So when you're teaching just recreational diving, oxygen doesn't become toxic until about 180 something. 84 is like the 1.4, and like 210 is like the 1.6. So we're not worried about it for recreational divers. But when you're breathing 40%, it absolutely becomes an issue, because it's within that realm of recreational diving. So you have to let them know that this is another gas you have to manage, and the function for that is MOD, so that they fully understand what that kind of stuff is. All right. So this sucks. I'm going to show you guys a better way to do that. Yep, these all suck. Memorizing these equations, these suck. Yeah, equivalent air depth. This is an equation that'll help you remember how to calculate equivalent air depths. If I ever needed to do this anymore, I would definitely Google it, because nowadays your computers do everything for you. Back in the day, when all you had were tables and things like that, this was important. But this is kind of gone by the way of the dinosaur. You might have to do it for your test. So I'm pretty sure it's on your equation sheet. So I wouldn't worry too much about dedicating these to memory.
Okay.
It's in our Nitrox log if you ever needed to know it. So what you use equivalent air depth for is if you're ever using a Nitrox, if you're using Nitrox and all you had was an air table, you would use this equation to convert your Nitrox mix to an equivalent air depth, and then use that air depth, that air table, with the equivalent air depth. Does that make sense?
Yeah, so you run the equation, whatever number you get, you look at the chart, and then
Yeah, and then you treat that Nitrox mix like it's an air at the equivalent air depth. That's it. Okay. Force pressure, gas solubility. This is Henry's law, and this is what I was talking about. Yep. This is all a given type. This is what I was talking about, right? Henry's law. It'll dissolve at the same amount at the same uniformly spread at the same equilibrium at the same pressures every time. Okay, so this is what it's telling you. At 1 atmosphere, it's going to be, or 0.25 is going to be 0.25. At 0.5, it's going to be 0.5. At 0.7, this would be 0.25. That's a typo. Oops. That should be 0.25, not 0.025. All right, it should be 0.5. So this is what this is saying, right? The combined sum of all the gases is going to be equal to the number of atmospheres in the gas.
so let's say if you were going up in the air. So
What's that?
0.75 bars, that means you're 25%, above the earth.
All this
right?
is trying to show you is that the gases dissolved, the pressure of the gas dissolved in the solution is going to reach equilibrium eventually after 5 half-lives of the ambient pressure that the solution is exposed to. And in diving, the ambient pressure that the gas is exposed to is the gas in the lungs. And the gas in the lungs is the pressure of the gas in the lungs is regulated by your second stage regulator, which is regulated by the pressure of the water around you, or the air when you get out of the water. The lungs are the low pressure point of your body when you're exhaling, and the high pressure point of the body when you're inhaling. But that's physiology. We'll talk about that later. All right, we'll talk about that later. Yeah, we will talk about this a lot more in depth in physiology. A lot more in depth in physiology. More in depth in physiology. Yeah, we'll talk a lot. So this goes into the decompression models. What you guys need, half times. I'm going to talk a lot more about this in physiology, right? But there are different compartments of tissues. A lot of computers will model your decompression times limits based upon the number of compartments your body it has modeled off of. Some of them have like 25 different compartments, some of them have 5, but your softer tissues usually have a faster on and off gassing rate, and then your harder tissues have a longer off and on gassing tissue rate. Your limiting tissues for the shorter time, for the deeper depths, are your short tissues, your shorter tissues, and the longer tissues, the shallower depths for your longer times are going to be your longer tissues, because those take a long time to off gas. We'll talk about that more in depth later. We'll talk about M values a little bit later too. Not too worried about these different algorithms. You can go in depth for algorithm for a long time. Table, yeah, don't care about these too much. Want to get into the wheel. Okay. All right, so we're going to talk about the wheel. How much time do I have left? Okay. If we have more time to talk about the M values and stuff like that, I will. Might talk about that next week. But I want to show you guys how to use, I got to use a different color. All right. How to use the wheel, which is one of the most useful things you can know how to use in for nitrox and all that stuff. For all those equations I was showing you that aren't that, that I thought weren't that great. All right, so at the top you have, oh man, all right, I'm doing this for you. VO2. Okay, partial pressure of oxygen. I'll even move it so it's in the middle. Okay, and then over here you have a fraction. Oh, needs to be fraction of oxygen, FO2, and that's in decimal form. So if it's at 28%, it's 0.28. Okay, then over here you have the depth. In atmosphere. Okay, so if you need to write down, depths in atmospheres equals, let's see, depth in feet divided by 33 plus 1, and then you can do depth in feet equals, let's see how I do this stuff real quick. It's going to be depth in atmospheres, 33 times the depth in atmospheres minus 1. So real quick algebra. That's how I always remember that. Right, so I move this guy over here, and I multiply both sides by 33. Okay, just to help me go back and forth. That's the hardest part about this circle is this section over here. Okay, so really easy. This is kind of like if you know Ohm's law, this is kind of the same concept. What you have to do is if you want to find partial pressure of oxygen, you multiply these two together. If you want to find a fraction of oxygen that you need, you divide partial pressure of oxygen divided by your depth in atmospheres. If you want to find the depth of your MOD, you divide your partial pressure of oxygen that you're using divided by the partial pressure the partial pressure that you don't want to exceed, and your fraction of oxygen, right? Remember, your two partial pressures that you're concerned about is 1.4 and 1.6, right? Planning and contingency. All right, so let's run through a problem or two. This one I'm going to do in pencil. All right, so say we'll do a first one. Our partial pressure. Maybe I'll try a thicker pen. Maybe it will help. My partial pressure. Okay, see, I'm diving a fraction of oxygen. I'm diving EA and 40 at a depth at this isn't even a thing, okay. 40 at, and we'll say, I don't know, 97 feet. No, 92 feet. And my question is, am I exceeding my MODs? Right? Or am I exceeding my MOD? Am I exceeding my safe PO2s? Right, so it's pretty easy on this one. It's going to be my fraction of oxygen is 0.4, 0.40, right, times 92. No, that's not going to work. I have to convert that to feet or to atmospheres. So it's going to be 92 divided by 33 plus 1. All right, that's 3.8. We'll put 3.78. All right, so I'm going to bring that down here. 0.4.
That's your atmospheres?
That's number of atmospheres, yep.
Yeah.
ATM times times 3.78. This is fraction of oxygen. This is number of atmospheres. So I'll bring up a calculator. All right, I have 3.78 right there. I'm going to multiply this by 0.4. So my PO2 is right in the middle of 1.4 and 1.6. So I'm exceeding 1.4. 1.4 is less than my PO2, which is less than 1.6. So I'm in the yellow zone, if you would, for that. Okay, does that make sense?
Yeah. So you wouldn't dive that then, right? Unless
You are
had-
in the contingency zone. You're risking it, but you'd probably be okay. But I wouldn't plan it that way. I would definitely plan it another way. Okay. The next thing I want to do.
I mean, but if you're a dive master and someone brought that with them and you had extra cylinders, you probably would switch out their cylinders.
I'd be like, nope, don't do that one, unless they insisted and they're like, I'm, blah blah blah, and this is, whatever. Like if that's what they're planning to do for like a decompression stop or whatever, yeah, that's probably okay because it's a resting decompression stop. But if they're doing decompression stops, then they probably, or know what they're doing. So, anyways, now let's say I wanted to find my MOD, right? So, oops, I'm fine. MOD. So I got a PO2. I want to plan for 1.4. Right, and the gas I'm breathing is 38.38. It's my fraction of oxygen. So what is my depth? I can do. So it's pretty easy. You're gonna take 1.4 divided by 38.38, and that's going to be equal to, get over here, 1.4 divided by 0.38. That's going to be equal to 3.68 atmospheres. All right, I got to convert that to depth in feet. All right, so I have to go depth in feet equals 33 times 6, oops, 3.68 minus 1. So we'll bring up this guy. So I'll subtract 1 from that. And I'll multiply that by 33. And that means at 88.5 feet. 88 point, I'll say 6 feet. So I'd probably round that out to a nice 88 feet or 85 feet, because that's more operationally sound. Is my MOD. Does that make sense? Sounds nice and easy.
Okay.
Okay. And then finally, figuring out, well, we just did that one. What is the best mix? Say I got a operating PO2. Best mix. Optimal mix. Oop. All right, so say I doing some really precise diving and I want to minimize as much surface interval as I can. And I need to really nail my mixes. Right? And I know exactly where I'm diving, and I know that the bottom is exactly 67 feet, or exactly I don't know, 89. No, I already know that one. 114 feet. Okay, so my depth is 114 feet exactly. 100. That was a good F. 114 feet exactly. That's not as good as an F. Okay, and I don't want to exceed 1.4, right, of a partial pressure. So now I gotta, I gotta convert that to atmospheres, right? So I'm gonna divide that by 33, and I'm gonna add 1 to it. So it's pretty easy. Pretty simple ratio to figure out the water pressure. I'm gonna add 1. That's gonna be 4.45 atmospheres. And then I'll just go ahead and put this over here. Simple math. 4.45 atmospheres. And then I'll do 1.4. 1.4 divided by 4.45. And then 31.4. 31.4 is my best mix for that first dive. And then my second dive, let's say my next second dive is 92 feet. 92 feet is my next dive, right? So I'm going to do 92 feet divided by 33 plus 1 equals 92 divided by 33 plus 1 equals 3.78. And again, I want to do 1.4. 1.4 divided by 3.78. And that's going to be a 37% mix. I see that right? Yeah, 37% mix. 37% mix. All right, so I would be my first dive is this dive, is that mix. My second dive would be that mix. Now I would make sure to mark those, very distinctly so I wouldn't, mix those bottles up. You wouldn't want this one to be your first dive and that one to be your second dive.
Yeah, because that mix on the first dive, you could get into oxygen.
Yeah, that one could make you convulse.
Yeah.
Yeah, that one could give you a CNS hit for sure. So that's how you use the Nitrox wheel. One of the most useful tools when you're talking about Henry's law, and when you combine that with Boyle's law, it's over here, right? And Dalton's law. When you combine all that stuff together, it gives you this Nitrox wheel, which a lot of people have a hard time with memorizing all those equations and going back and forth. But if you do it like this, it's real easy to remember how to do all that stuff. You just have to remember your depth is in atmospheres. So I got to put this stuff up here.
Who came up with the wheel?
I saw it on YouTube at one point, and I was like, that's a really good idea. So I stole it. But it's been around for a while. I saw it in like 6 or 7 different places on YouTube. So I stole it. But it's a simple, it's just like Ohm's law.
Yeah.
But anyway, we're at 1 minute and 50 seconds. So if you guys want to go over, I'll send you some more questions involving this. These will be easy homework. And then I shared the last set of questions for that. If you guys want to run through that first one we went through again. And then that second set of questions is a little more difficult if you want to challenge yourself on that. If you get, like I said, if you guys can do these questions, any of the math questions you're going to come across on the exam is going to be stupid easy. So, and what I'm really going after here is I don't expect you guys to be like whizzes on math. I just want you to understand the concepts, so that when people have like simple questions, you can explain them intelligently, so that they have confidence in you as a dive master.
Do you have to be a whiz at all this stuff to get your instructor?
It helps. Don't have to be as good as me, but
no one's as good as you, John.
That's not true. There are plenty of people that are better than me. But I just don't teach as much as I used to anymore, that's for sure. I'd love to start teaching again, though, more than I do now. But hey, what are you doing, Terrell? What are you doing Saturday? You working? Darrell, you there still? Oh well, I think he's zoning out. Anyway,
You got me?
yeah, you working Saturday?
Yes.
When's your next